Okay, today we are going to discuss a new theorem in measure theory, and the theorem is called countability subadditivity of outer measure. Okay, so the theorem says that theorem is, this is very important and a lot of time we use it, that if A is contained in the union of KAK, okay, so means if we have sequence of the sets A1, A2, A3, and then we have another set which is the contained in the union of all those sets, so then the outer measure of A is less than sum of K is equal to 1 up to infinity the outer measure of AK. Okay, so that's actually we are gonna prove this thing. Definitely to prove this thing, so if the right side sum is actually infinite, then there is nothing to prove, right? This is very obvious. Then there is nothing to prove. So surely we will assume that the right hand side sum is actually finite. So in particular this is finite for all K. Okay, now what we are gonna do, since we have A1, A2, A3, A4, so we, for each set we will have the cover. So we can say that okay, let epsilon greater than to 0. Why, you will see in a while. That we have a positive number epsilon, then there exists the sequence of open interval which we denoted ijk, such that each ak is contained in the union of j is equal to 1 up to infinity ijk. So from here it is clear that okay, a1 is contained in the union of j ij1, and a2, because this is a1 a2, for every a1 we will have a cover, so a2 is contained in union of j ij2 up to so on. So that's why we say that ak is contained in the union of these open intervals. So for each k we have a cover. So in general we say that okay, ak is covered by the union of j is equal to 1 up to infinity ijk. Alright, but definitely then there exists ak such that this, and but we want one more condition, and then one more condition is that the sum of the j is equal to 1 up to infinity and length of all those interval should be less than or equal to the length of the outer measure of the ak and plus epsilon divided by 2k. That's we just assume, because that's gonna help us. So now if we have this equation, this inequality, then from there we can easily move on. Okay, so easily, so now since a is contained in the union of k is equal to 1 up to infinity, this is countable many ak, and then clearly ak is contained in the j is equal to 1 up to infinity ijk. Okay, so which we can write down union of kj is equal to 1 up to infinity ijk. So from there we can say that a is contained in the union of kj is equal to 1 up to infinity ijk. Okay, now since okay, so since we know that a is the outer measure, okay, and outer measure is actually the infimum, and the infimum value is less than the sum of the length of the open intervals that contains the set A. So clearly, so then we have the outer measure of A is less than equal to the sum of kj is equal to 1 up to infinity length of ijk, which we can write down sum of k is equal to 1 up to infinity, sum of j is equal to 1 up to infinity length of ijk. Now since we can rearrange the terms because the length of ijk is positive, so suppose if it was negative, then you cannot do that, because then the value of the series can be different. But now since the length of the open intervals is positive, so definitely every term in the series is positive, so we can rearrange the term and we will have the same value. So from here, but now clearly we have this length is less than, since we assume that k is equal to 1, that the sum of j of length of ijk is less than the ak, the outer measure of ak plus epsilon divided by 2k. So now what is this? So this is sum of k is equal to 1 up to infinity the outer measure of ak, and plus what is the sum? The sum of epsilon divided by 2k over k is epsilon. So now from there we got this thing. Okay, so from there we got the outer measure is less than sum of k is equal to 1 up to infinity ak plus epsilon. Okay, so okay, so we know that, so if for epsilon greater than or 0, there is just note. Okay, so we have x is less than y plus epsilon, then clearly x is less than or equal to y. So suppose this is my x, this is my y, and this is my y plus epsilon. So if x is less than y plus epsilon, then we can, what can we say? Then we can say that x is less than or equal to y. Okay, so now so from a is less than or equal to sum of k ak plus epsilon, we have a is less than or equal to sum of k ak, and that was our proof. Okay, that was our proof. So but now a was contained in the union of k ak. So by the monotonicity we already proved that the outer measure of a is less than the outer measure of ak, and then definitely this is less than, as we already proved that sum of k is equal to 1 up to infinity ak. So our actual result is that the union of k is equal to 1 up to infinity ak is less than equal to sum of k is equal to 1 up to infinity ak. That is our actual proof. This is called the monotonicity. This is called the subadditivity of the outer measure. Okay, so this is subadditivity of outer measure. I hope so. In short, we can say that the A1 union A2 union A3 up to so on is less than or equal to sum of k is equal to 1 up to infinity outer measure for each. So always if we take the union of all these sets and we take the outer measure, that will be always less than the sum of the outer measure of each set. So that is called countable subadditivity. That is very important, everywhere we use it. And